Alright, silly people, here's the situation. Uh, Griffiths is giving us these two matrices, A and B, and he's going to ask us to do a bunch of stuff with them. So, the first thing he wants us to do is to just add them up, A plus B. Um, the way to add matrices is literally just to add up each element of the matrices, so you add the top left component with the top left component of the other one, and so on for every single component of the matrices. So we've got 2 minus 1, which makes 1. We've got 1 plus 0, which is 1. We've got I minus I, so 0. 2 plus 0, so 2. 0 plus 1, so 1. 3 plus 0, so 3. 2i plus I, so 3i. Minus 2i plus 3, so 3 minus 2i. 2 plus 2 is 4. And yeah. The next thing that Griffiths asks us to do is to multiply the matrices together. And I do like to actually write out both matrices if that's what I'm going to do, uh, just next to each other so I can see what I'm doing. But to multiply matrices together, it's a little bit of a process. But basically, for each element of the matrices that are being multiplied, so the resultant matrix, you take, this is going to be the multiplication of the top row of the first matrix, so top row of A, times the first column of B, right? So it's pretty much just a dot product of those, treating the top row of A as a vector and the first column of B as a vector, and taking the dot product of them. So it's pretty fun stuff. So we've got minus 1 times 2 makes minus 2. 1 times 0 makes 0. I times I makes I squared. The next element down is the dot product of the second row with the first column, right? So it's 2 times 2 makes 4. 0 times 0 makes 0. 3 times I makes 3i. And then the final column down is going to be the dot product of the third row of the first matrix with the first column of the second. So we've got 2i times 2 makes 4i. We've got minus 2i times 0, which is 0, and then 2 times I, so plus 2i. Whenever you want to move to the next column of the product matrix, you have to now just do whatever row you're on, and then multiply it by whatever row you're on for the first matrix, and multiply it by whatever column you're on for the second matrix. So for this element here, we have to do the first row of A dotted with the second column of B, right? So it's minus 1 times 0, which is 0, 1 times 1, which is 1, I times 3, which is 3i. And I'm kind of done explaining the whole process, but you should get the picture now. So 2 times 0 is 0, 0 times 1 is 0, 3 times 3 is 9, 2i times 0 is 0, minus 2i times 1 makes minus 2i, and 2 times 3 makes 6. Minus 1 times minus I makes I. 1 times 0 makes 0. I times 2 makes 2i. 2 times minus I will make minus 2i. 0 times 0 is 0, 3 times 2 is 6. 2i minus I is minus 2i squared. Minus 2i times 0 is 0, 2 times 2 is 4. Okay. Now let's deal with all of those I squareds and do some addition. So I squared is minus 1, so this is minus 3. We've still got 4 plus 3i here. This adds up to 6i. 1 plus 3i up top. We've got 9. We've got 6 minus 2i. I plus 2i makes 3i. 6 minus 2i is just, 6 minus 2i. Minus I squared is positive 1, so we actually have 2 plus 4, which makes 6. And that looks good to me. Okay. The next thing that Griffiths asks us to do is to get the commutator of A with B, which is defined as being the product of the two matrices A and B minus the product of B with A, which they are different, if you didn't know. So I'll write out what we just got for AB, but we're also going to have to get BA in much the same process as before. So we've got B, which again was 2, 0, I, 0, 1, 3, minus I, 0, 2, times A, which was minus 1, 2, 2I, 1, 0, minus 2I, I, 3, 2. Okay, so let's carry out the multiplication of the two matrices once I'm finished writing this one again. And then this is going to be minus 2 times minus 1, which is minus 2. 0 times 2, which is 0, minus I times 2i, which is minus 2i squared. 0 times minus 1, which is 0, 1 times 2, which is 2, 0 times 2i, which is 0. So just 2 for that one. I times minus 1, which is minus I, 3 times 2 is 6. 2 times 2i is 4i. 2 times 1 is 2. 0 times 0 is 0. I times minus 2i, or minus I times minus 2i makes positive 2i squared. This whole thing is 0. Then I times 1 is going to be just I. 3 times 0 is 0. 2 minus 2i is just minus 4i. I times 2 is 2i. 0 times 3 is 0. We've got another minus 2i here. Then we've got 0 times I, 1 times 3, 0 times 2, I times I, so I squared, 3 times 3, so 9, 2 times 2, so 4. Okay. We can start simplifying the resultant matrix before we try and subtract. So 2 minus 2i squared, so minus 2 plus 2, so 0. 2 is still 2. 6, this is now 6 minus 3i, or 6 plus 3i actually, because 4 minus 1 is 3. 2 minus 2, so 0 here, still 0 here. I minus 4i makes minus 3i. And then this is 2i minus 2i, so still 0 there. 3, that's minus 1 plus 9 plus 4, so 12 here. And now we can just subtract off every element here. So 3 minus 0 is still minus 3. Uh, 4 plus 3i minus 2 is 2 plus 3i. 6i minus 6 plus 3i is going to be 3i minus 6. We've got 1 plus 3i. We've got 9. 6 minus 2i plus 3i is going to be um, just 6 plus i. Then we got 3i. Then we got 6 minus 2i minus 3. So 3 minus 2i. 6 minus 12 is minus 6. The next thing Griffiths is going to have us do is do the transpose of A. So let me write out what A was again so I can have a little bit of clarity. It's going to be minus 1, 1, I, 2, 0, 3, 2i, minus 2i, 2, right? The idea of the transpose is you just replace um, every nth row with the nth column, right? So in here, the first column of the transpose is going to be identical to the first row of the matrix. So it's going to be minus 1, 1, I, right? Second column is going to be the second row. So we have 2, 0, 3. And then finally, the third column is going to be identical to the third row. So it's 2i minus 2i, 2, right? The complex conjugate of a matrix is you literally just take the complex conjugate of every element of the matrix. So we take our A, we just do the complex conjugate of every element. That's supposed to be a 2 there. 1, 0, 2i minus I, 3, 2. The Hermitian conjugate, or A dagger, is just the complex conjugate of the transpose, or vice versa. So we just take our transpose matrix, which we just calculated, and do the complex conjugate of it. So minus 1, 1, minus I, 2, 0, 3, minus 2i, 2i, 2. Awesome. Now Griffiths wants us to do the determinant of B. So that is usually just denoted by a straight line around the matrix. So instead of the parentheses, and that'll close off there because it is just kind of like an absolute value of the matrix. And so the way that Griffiths teaches you to do this is rough. I'm going to show you the way that my Calculus 2 teacher taught me how to take determinants of three-dimensional matrices. What you do is you just write out the first and second columns again outside of the determinant, and you just multiply along the diagonal lines, right? So you multiply this here and multiply it again with this element here, and you do the same here, multiply, multiply, and still here, multiply, and then multiply. And you take the result of all of those multiplications and you add them up. So for us, that's going to be 2 times 1 times 2, which is 4. 0 times 0 times I, which is 0. Minus I times 0 times 3, which is 0. Cool. And then you go the other way, and now you multiply up and to the right. So you multiply this guy with this guy, and this guy with this guy. Same here. Just going up and to the right for the diagonals. So we have I times 1 times minus I, which is minus I squared. But then we have to subtract this multiplication off from the first one. So minus I squared. So plus I squared. And then this is 0 because there's a 0 in there, and same with here. So the determinant is just 4 plus I squared, which is 4 minus 1, which is 3. Right. Also, the way that Griffiths kind of describes the way to take an inverse of a matrix is not great. So I'm going to teach you the way my algebra teacher, or my linear algebra teacher, wanted me to do inverse matrices. So what you do is you line up your matrix, which again B was 2, 0, I, 0, 1, 3, minus I, 0, 2. And then you set it next to the identity matrix of the same dimension, which is 3 here. So 0, 0, 0, 1, 0, 0, 0, 1. And then you do row operations on both matrices simultaneously until the left side matrix looks like the identity matrix. Right. So to do that, we have to, first of all, let's scale the matrix on the left and on the right. So I want to right now make R1, row 1, that is, I'm going to divide it by 2. Okay. And I'm also going to divide R2 by nothing because I think it's the way that it is. But I'm going to divide R3 by I. And that is just going to make it so that the leading terms are going to be 1, 0, 1. This is going to be 0, 1, 3 over I, which is minus 3I. This is going to be minus I over 2, 0, and then 2 over I makes minus 2I. And then on this side, we have 1 half, 0, 0, 0, 1, 0, 0, 0, minus I. Cool. Now I want to subtract the first matrix, or the first row from the third. So R3 is going to be transformed to R3 minus R1, right? So we've got 1, 0, 0, 0, 1, minus 3I, minus I over 2, 0, and then minus 2I plus I over 2, right? And then we're going to do the same thing to the right hand side of this matrix. So, and yeah, so we've got 1 half, 0, 0, 0, 1, 0, minus 1 half, 0, minus I. All right. Now row 2 is already looking how we want it. So I'm actually going to now, let's just simplify the matrix for now, because I think it'll be good for us to do so. So I over 2 minus 2I is just minus 3I over 2, right? Or it's 0 here, minus 1 half, 0, 1, 0, 0, 0, minus I, right? Now I'm going to scale row 3 again. So I'm going to take row 3 to row 3 over minus 3I, which is going to change this leading term to 1, and then we got I over 2, 0, and then just 1 half here. And then this is going to be 1 half, 0, 0, 0, 1, 0. So it's minus 1 half divided by minus 3i. So it's going to be 1/6, 1 over 6i. So just minus I over 6. And then we've got a 0 here, and then a plus 1/3 here. Cool. Now let's do row 3, transform it to row 3 minus row 2, so we can get rid of this 1. So we've got 1, 0, 0, 0, 1, 0, minus I over 2, 0, 1 half, 1 half, 0, minus I over 6, 0, 1, minus 1, 0, 0, and then just 1/3 here. Finally, let's scale row 3 one last time by multiplying it by 2. So now we have 1, 0, 0, 0, 1, 0, minus I over 2, 0, just 1 here, and then 1 half, 0, minus I over 3, 0, 1, minus 2, 0, 0, 2/3. And then now we go to row 1 and we add row 3 plus I over, row 3 times I over 2, is what I should say. That way the last element in the first row will be 0 now. So on the left hand side we now have the identity matrix. And then on the right, we've got 1 half, 0. Actually, it's going to be 1 half minus I over 3 times I over 2. So let's write that out. 1 half minus I squared over 6 is what it's going to be. And then everything else should be fine. It's going to be 0 minus I, so it's just minus I on here. This is still 1, this is 2, we've got 0, no we don't, because we have I over 3 here. What I'm doing is I'm adding row 3 times I over 2, just to be clear. But yeah, this should be fine now. So now what is on this side is now the inverse of b. So we've got inverse of b is equal to 1 half plus 1/6, which is 4/6, which is 2/3, and then 0, and then minus I over 3, and then minus I, and then 1, and then minus 2, and then I over 3, and 0, and 2/3, which we can write instead by pulling out a factor of 1/3. Just 2, 0, minus I, minus 3i, 3, minus 6, I, 0, 2. Okay, so that was a hassle, but we got there in the end. The last thing that, or I guess not the very last thing, the next thing that Griffiths wants us to check is if we multiply the matrix B by its own inverse, that it equals 1. So let's just do the multiplication of B with its inverse. So B was 2, 0, I, 0, 1, 3 minus I, 0, 2. The B inverse, we just found it was 2, 0 minus I, minus 3I, 3, 6, I, 0, 2, and then it's all multiplied by a 1/3. So 1/3. So that's going to be 2 times 2 is 4. 0 times 0 is 0. Minus I times minus I is going to be plus I squared. 0 here, 0 there, 0 here. So just 0 for that element. 2I, 0 minus 2I, minus 6I, minus another 6I. Is that right? I didn't write that right. This is a minus sign here. So it's actually plus 6I. And then just 0 times minus 3I is 0. We've got 3 here, and then we've got 0 again, so it's just 3. Then I times minus 3I is minus 3I squared. 3 times 3 is 9. 2 times minus 6 is minus 12. We've got 2 times I, which is 2I. 0 times 0, minus 2I. 0 times I is 0. 1 times 0 is 0. This whole thing is 0. I squared plus 2. Or plus 4, actually. Haha. And then the whole thing is divided by 3. So just turning all the I squareds into 1s, we've got 4 minus 1, so 3 here. We've got 0. These cancel out, that's 0. These cancel out, that's 0. 3, we've got 3 plus 9 minus 12, which is 0. These cancel out, 0. 0, 4 minus 1 is 3. The whole thing's divided by 3. We can carry out that division, so we get 1, 0, 0, 0, 1, 0, 0, 0, 1. So we're good. They made the identity matrix after all. The last thing that Griffiths asks is, does the inverse of A exist? So inverses for matrices only exist if the determinant of the matrix that you're trying to inverse is not equal to 0, right? If the determinant is 0, then the inverse does not exist. So what we have to do right now is we just have to do the determinant of A. And if it's 0, then we can conclude that it does not have an inverse. So I'm going to do the same thing where I write out the rows or the columns down here and do the diagonal multiplication again. So we've got 0, 6i, and then minus 4i squared. Bam, bam, bam. That's going to be positive 6i. So which you have to subtract off. And then that just looks like 4. I just realized it should be 4i squared. So the 6i will cancel out the 6i. 4i squared is just going to be, or minus 4i squared is just going to be positive 4. We have the minus 4, which those cancel out, so it's 0. So the inverse of A does not exist. Awesome.